Hello students, welcome to my channel again, and thank you for just supporting my channel and enjoying my video lectures. And today I will continue my discussion on the operators that was being discussed in the previous lecture. So in the previous lecture we discussed about certain basic quantum mechanical operators. One was the linear momentum operator and another was Hamiltonian operator, which was giving the eigenvalues as energy of the particle. So today we will discuss some more things related with the operators. The first thing is, what is the operator for position? Position operator. So position operator for a component of position of a particle is that component itself. Let us say I want to write the operator for component or x component of the position of the particle. Then that operator is written by x cap, and x cap is nothing, it is x itself, where x is the position coordinate along x axis and x cap is the momentum for the position coordinate, x coordinate of the position. Similarly, operator for y coordinate of the position will be y itself, and component for z coordinate will be equal to z itself. Similarly, what are the operators for potential energy? Potential energy operator. So potential energy operator U cap is again just like position operators. It is equal to potential energy itself. For example, let us say we are discussing the equation of a one-dimensional harmonic oscillator. Then the potential energy operator for a one-dimensional harmonic oscillator will be equal to half k x square, where k is the spring constant and change in length is represented by x. Similarly, what is the operator for kinetic energy? So it is represented by capital T cap. So kinetic energy operator is actually minus h cross square upon 2m and del square. These are the some additional operators which students must remember for solving various numerical problems in the chapter of this quantum mechanics. So these were certain different operators I wanted to share with you. Let us move to the next topic. The next topic is related with the normalization of a wave function. Normalization of a wave function. What is normalization of a wave function? This topic originates from the physical significance that was given to the square of magnitude of wave function by Max Born. According to him, square of magnitude of the wave function at a point is directly proportional to probability density. Let us say particle is moving in a three-dimensional space, and at any point, let us say this is any point, I draw a small region around that point. Suppose this region has volume dV, and in this region the probability of finding the particle is dP. Then this dP by dV is called probability density. It is called probability density. So according to Max Born, square of magnitude of the wave function is directly proportional to probability density. Now, if I want to just convert this proportionality into an equality, then I would be able to write this as psi magnitude square is equal to some constant n and dp by dv. N, I have just taken it to be n. You can write this constant as c or something else, whichever you wish. and there is no way hard and fast rule that you will always write this to be n. In fact, in numerical problems, so we usually take any unknown constant which should be actually preferably a multiplier constant, to be a normalization constant. So this constant which is appearing from Max Born's interpretation of the wave function, this constant n which appears in this equation 1 is called a normalization constant. Now, this normalization constant may have some unit or may not have some unit. Why? Because left hand side of this equation will have different units depending upon the type of the problem. It may be 1 divided by square root of length in one dimensional motion. It may be having all different units in 2 and 3 dimensional motion. So this constant n is chosen in such a way that equation 1 is dimensionally balanced, means n takes care of the account of the fact that the left hand side and right hand side should have same units. Moreover, if this value of n is equal to 1, let us say if this value of n is equal to 1, then equation 1 will become psi magnitude square is equal to dp by dv. That is, psi magnitude square will be exactly equal to probability density. In such a case, if this happens, that n becomes equal to 1 and psi magnitude square exactly becomes equal to probability density, then psi is called a normalized wave function. Then such a wave function is called normalized wave function. On the other hand, if psi magnitude square is not equal to dp by dv, or you can say if n is having some value other than 1, then such a wave function n is not equal to 1, then such a wave function psi is called unnormalized wave function. So a wave function is said to be normalized if psi magnitude square is exactly equal to dp upon dv. That will lead to normalization constant value equal to v1. And it is said to be unnormalized if psi magnitude square is not equal to dp by dv. However, it will always be proportional to this value. Kindly remember this. And value of n will not be 1. Then such a constant, in such a case, a wave function is called unnormalized wave function. However, it is always possible. It is always possible to obtain normalized wave function from unnormalized wave function by multiplying psi with some suitable number or suitable constant. So why is it so? Why this statement I have written that it is always possible to obtain a normalized wave function from unnormalized wave function by multiplying with some suitable number? It is due to the fact that wave function psi, it is actually the solution of Schrödinger equation. SE stands for Schrödinger equation, and Schrödinger equation is a differential equation, and there is a property of differential equation that if a any function psi is a solution of a differential equation, then any constant multiplied to psi is also a solution. So therefore, if I solve a Schrodinger equation, and after solving a Schrodinger equation, and if I solve a Schrodinger equation, and after solving a Schrodinger equation, suppose I obtain certain wave function psi, then I check it for some probability, then I check it for normalization. Just I want to find this integration, that psi magnitude square is equal to dp by dv or not equal to dp by dv. If it is not equal to dp by dv, then my wave function will not be a normalized wave function. However, Schrodinger equation is a differential equation. I can multiply it with some constant, and that constant multiplication will still make the new wave function a solution of the Schrodinger equation. And however, this new wave function, which is obtained by multiplying psi with some constant, will be a normalized wave function. Let us just take an example. Okay, suppose I obtain psi, some wave function psi. Let us say I obtain some wave function psi, which is the solution, which is obtained by solving Schrodinger equation. Since it will have some mathematical expression, I would give you some example after that. Since it will have some mathematical expression, let I assume that psi magnitude square is known to us. This will be the primary condition. So I must be able to write the mathematical expression of psi, which I would have the knowledge because I have already solved the Schrodinger equation. Then I should have the value of psi magnitude square known to me. This will also be possible. Since I know psi, therefore I can easily calculate psi magnitude square. Then what I will do, I would just find this value. Find psi magnitude square dv from minus infinity to plus infinity. Suppose this value comes out to be something, let us say some minus infinity to infinity psi magnitude square dv comes out to be something, let us say n. Now this can be written like this. I can write it like this: minus infinity to infinity psi upon square root of n magnitude square dv is equal to 1. Now you can see both of these equations are equivalent to each other. And however, in this case I have written this n on the left hand side because it is constant. I can write it inside the integration. Now I can put psi divided by square root of n, a new wave function psi dash, so that this equation becomes minus infinity to plus infinity psi dash magnitude square dv is equal to 1. Now this answer is 1, which means that psi magnitude dash square is equal to dp by dv exactly. Psi magnitude square was not equal to dp by dv, otherwise the answer of this integration would have been 1. It came out to be something, let us say that something was L. Then I took this n on the left hand side, then psi upon n dash n magnitude n square root, I called it to be a new wave function psi, and this integration is equal to 1, obviously this quantity is now exactly equal to dp by dv, because if I take this it to be dp by dv here, this will become dp by dv will get cancelled. The integration of dp from minus infinity to plus infinity will be 1. That is the total probability. Therefore, psi dash, which is equal to psi divided by square root of n, is normalized. So I have normalized the wave function by just evaluating an appropriate constant square root of n, which can be divided, or in certain conditions it can be multiplied to the wave function, so that we get in an unnormalized wave function converted into normalized wave function. Let us take a practical example now to check. Suppose this question is asked from us that, let us say there is a particle in a one-dimensional box. This one-dimensional box starts from x equal to 0. It ends up at x equal to L. There is a particle of mass m which can either move toward plus x-axis or toward minus x-axis. It cannot move in any other direction, and moreover it cannot go to the left of x equal to 0, it cannot go to the right of x is equal to L. The wave function of such a particle is given to us. Psi is equal to a sine n pi x by L. This is given to us. Let us say we will be solving this during the applications of the Schrödinger equation. For the time being, just remember that this wave function is the solution of Schrödinger equation for this problem. I will formulate the Schrödinger equation for this problem, then I will solve it, and we will notice that the wave function obtained will be this one. Here a is a constant of integration. By this constant of integration comes during the solution of the Schrödinger equation, which is a differential equation, and we want to convert this wave function into a normalized wave function. We assert that a is chosen in such a way that psi magnitude square is equal to dp by dv exactly. So I will find that appropriate value of a which will make psi magnitude square equal to dp by dv exactly, and if this happens, then this wave function given in equation number 1, it will become normalized. Let us see how. Now if I make this assertion and I just test this assertion here, therefore my dp will be simply equal to psi magnitude square dv, and since the particle cannot go out of this region 0 to L, therefore obviously integration of dp from 0 to L must be equal to 1. So since particle is always present from 0 to L, the total probability of finding the particle from 0 to L is always equal to 1. Okay, let us now do this integration. The value of dp from 0 to L, the value of dp from this equation is psi magnitude square dx, and that is equal to 1. Sorry, I wrote here dv by mistake. Actually it should have been written dp upon dx, because this problem is actually one dimensional problem. So this is equal to 1. Now put the value of psi magnitude square. This will be equal to a square sine square n pi x by L, and dx is equal to 1. I can take a square outside upon 2 0 to L. There I can apply this mathematical formula. It will become 1 minus cos 2 n pi x by L and dx upon 2 I have written already outside, and this is equal to 1. When I will solve, this integration will become L, and this will give me 0. So therefore a square upon 2, it will become L minus 0 is equal to 1, and therefore a will be equal to square root of 2 by L. So now this value of a is suitable for us. If I choose a equal to this, that is 2 divided by square root of L, and I insert this value of a in 1, then wave function psi is equal to 2 divided by L square root sine of n pi x by L. Then this wave function becomes normalized. For any other value of a, this wave function will not be normalized. So this is an example where I have shown you how to convert an unnormalized wave function into a normalized wave function. So let us now discuss last topic of today's lecture, that is about Hermitian operators. Hermitian operators. Okay, an operator is said to be Hermitian if it satisfies this property: minus infinity to infinity psi m star a cap psi n dv is equal to minus infinity to infinity psi m a cap psi n star dv. In this equation 1, star actually denotes complex conjugate. So if any operator operating on two different wave functions of a particle satisfies this property, then such an operator is said to be Hermitian operator. So what is the importance of Hermitian operators? What is the importance of Hermitian operator? So let us assume that let a cap is Hermitian. In order to understand the importance of Hermitian operators, I have to assume that there is certain operator which is Hermitian. If it is Hermitian operator, then a cap satisfies equation number 1. So this equation is satisfied by a cap because a cap is Hermitian operator. So now we assume that both of these wave functions are identical. Let us say I assume psi m is equal to psi n. Say both of these wave functions are identical. Now if I put this value in 1, I would get integration minus infinity to infinity psi n star a cap psi n dv equal to minus infinity to infinity psi m n actually a cap psi n star and dv. This is equation number 2. Now let us say that the eigenvalue equation of a cap on psi n is given by this. Suppose a cap psi n is equal to alpha n psi n, where alpha n is the eigenvalue. Means when a cap operates on psi n, then we get same wave function psi n multiplied by some constant of the system, and that constant is, let us say, alpha n. If I put this value in equation number 2, I would get integration minus infinity to infinity psi n star alpha n psi n dv equal to minus infinity to infinity psi n star alpha n star and dv. Now I can take alpha n and alpha n star out of the integration on both of the sides. So it will be alpha n integration minus infinity to infinity psi n star psi n dv, and it will be equal to alpha n star integration minus infinity to infinity psi n star and dv. So this will be alpha n minus infinity to infinity psi n magnitude square dv, and it will be equal to alpha n star integration minus infinity to infinity psi n magnitude square dv. I can take this term to the left hand side, so this will become alpha n minus alpha n star and integration minus infinity to infinity psi n magnitude square dv equal to 0. This gives me either alpha n minus alpha n star equal to 0 or integration minus infinity to infinity psi n magnitude square dv equal to 0. However, this is not a possibility. This quantity cannot be 0. I reject it on the grounds by using some logic that this quantity psi n magnitude square is actually proportional to the probability density, and if it is proportional to the probability density, so it is not 0, because particle is present in somewhere in the universe, because the limits of integration are minus infinity to plus infinity. So particle has to be found within somewhere within the universe. So this integration cannot be 0. I am left with only one option, that is alpha n minus alpha n star is equal to 0. That gives me alpha n is equal to alpha n star, which ultimately means that alpha n is a real number. So that gives me the significance of the Hermitian operators. So I would write the significance of Hermitian operators here, that the eigenvalues of Hermitian operators are always real. So this is a very good thing related to the good property of Hermitian operators, because actually we will always be solving Schrödinger equation, and we will be then getting some wave function, and then we would be interested in calculating various parameters of the system like position, energy, momentum, linear or as well as angular momentum, and other physical parameters of the system. And we know that the physical parameters of the system are obtained by applying suitable operator on the wave function, and then we solve the eigenvalue equation. However, in certain cases it may happen that we are just using our effort in solving the eigenvalue equation of the system by using suitable operators, and in the end we may get complex eigenvalues, but complex or imaginary eigenvalues are not measurable, although these can be calculatable, and if these are not measurable, then these are not really useful for us. So Hermitian operators will ensure that the eigenvalue problem that we are solving, which is taking so much time on the computers, it will consume lot of energy of the computers, it will kill lot of time, because the problems are very difficult to handle on the pen and copy. So therefore, if we use Hermitian operators, it will be ensured that the eigenvalues that we will obtain after solving eigenvalue problem will always be real. So this is the basic important property of Hermitian operators. So I would stop here now. This is all about the operators that I wanted to discuss with you in this lecture, and we would be just we have just made a base for starting the Schrödinger equation. In the next lecture we will discuss more about quantum mechanics, and hopefully we will be just discussing Schrödinger equation and its applications in the next lecture. Till then, it's goodbye from me. Thank you. Thanks a lot.